Alrighty, lads and ladies, welcome back to Calc 2. Today we are going to continue talking about sequences, and it is a big day. We have quite a few important theorems to cover, a handful of somewhat challenging examples to work through. Before that, a word on your exams. I know that you guys are anxious for those, and I'm sorry I haven't been able to get them to you just yet. Having a problem with the iPad that I use to mark these things. So when I first started teaching online, I would type all of the comments in on the written work, and that was the way I gave you feedback on the tests. The college, out of its generous budget, gave me an iPad to do that with over the summer, so I can write directly on the thing, which is very nice. But what I discovered as I was working through the tests is that the comments aren't saving, and that's a problem. So I'm trying to figure out what to do. I've talked to Santa Fe IT. They're working to see if they can get the issue fixed. But if not, I'll just go back to doing what I used to do and type the comments. I'm just trying to avoid doing that because it's a pain in the ass. But they will be done here as soon as they can. I'm going to start just going through and typing the comments today if I don't get a solution back from the IT people. So that's where we're at with that. I know it's been longer than we said it would be, but I will promise you that that it'll be done within a day or two. If I have to type the comments instead of writing them, it will take longer. So I cannot promise that it will be done today, but I'll begin going through and typing the things today rather than trying to mark the exams directly. All right, let's get to it. This is MAC 2312, section number 004, which is Calc 2, and the date today is the 16th of February. And what we're doing today is more sequences. So this is 11.1 revisited. 11.1 redux. We know now what sequences are, and we have a notion of convergence for them. We know that in order to discuss whether a sequence converges or diverges, we need to take the limit as n goes to infinity. That is the game. I mentioned that the primary tool here, we have this theorem, namely that if f of x is a function, and when you plug in n, you get an, meaning if you swap the variable from x to n, that function becomes your sequence. Then the limit as n goes to infinity of your sequence is the same as the limit as x goes to infinity of your function. There's a picture that goes with this. So let's do it like this. We'll say if your sequence is looking something like this, right, where the terms of the sequence are getting closer and closer and closer to L, and you think that limit of that sequence is L, then the function f of x would look something like this. That's what this condition that f of n is equal to an tells us. So if all the dots that represent the graph of the sequence are stuck along the blue curve, then wherever the blue curve is going, so must go the dots. That's the idea. So this is the graph of f. we mentioned the other day that you cannot differentiate a sequence. It really doesn't make sense to talk about the derivative of a sequence because there's no notion of a tangent line to the sequence. But there is a way to differentiate the blue curve, right? There is a notion of tangent line at this point for the blue curve. And so what this theorem does is it lets us kind of say, all the stuff that we learned about limits at infinity in section 2.6 regarding functions of a continuous variable can be applied to sequences by kind of, instead of thinking about the dots, thinking about the curve. In practice, so I'm going to do one example where I employ this theorem in a fully careful and rigorous way. But most of the time in practice, we will be a little hand wavy here. So let me show you exactly what I mean. An example of a sequence that we might have trouble working with, we could say, find the limit as n goes to infinity of an, where an is something like n times e to the negative n. The natural thing, of course, is just to write down that limit. So that would be lim n to infinity of an equals lim n to infinity n e to the negative n. And the issue here is that as n goes to infinity, of course, this first piece goes to infinity. And I'm going to put this in little quote bunnies. This is my notation for I'm not responsible. This is kind of bullshit. The n piece here goes to infinity. What does e to the negative n do as n gets larger and larger and larger? In other words, what is e to the negative infinity? Yeah, very good. That's 0, right? If you take e and you raise it to a very large positive power, you'll get a large positive number out. If you take e and raise it to a large negative power, you will get a very small positive number out. So this would be like infinity times 0, and that's a problem. What is infinity times 0? Does anybody know what that is? This is a bit of a trick question. Yeah, I'm getting a lot of conjectures that infinity times 0 is 0. Infinity times 0 is an indeterminate form. So it's true that in this case, we're going to get 0 out, but it's not true in general. It's not always true. Think of infinity as really, really big number. Think of 0 as really, really small number. If you multiply really, really big number by really, really small number, you could get a bunch of different things. It depends on how big the big number is and how small the small number is. Since these are both showing up in the context of a limit, we cannot say what infinity times 0 is in every situation. So this is what's called an indeterminate product, which is a specific type of indeterminate form. And you learned about these in section 4.3 of Calc 1, where you learned the thing called L'Hopital's rule. So there is a way to handle indeterminate forms and indeterminate products that is careful and rigorous, but it requires differentiation. It requires taking a derivative. Remember how L'Hopital's rule works? You take the derivative of the top, derivative of the bottom, you try taking the limit again, see what happens. Sometimes you do it 2 or 3 times. But because the object I'm playing with here is a sequence, the dots, I can't really take its derivative. It doesn't make sense to say I'm going to take the derivative of a sequence if you think about what a derivative really is, because it's defined in terms of limits as h goes to 0, and you can't do that for a sequence because it's only allowed to take whole numbers as its input. But the idea here is that instead of thinking about the sequence, just the dots, we can think about the curve. So we know we're going to need some L'Hopital's rule. But that would require derivatives. And we know that it doesn't really make sense to talk about taking the derivative of a sequence. That was something we discussed last time. So instead, we use our theorem here. What we're going to do is let f of x be the function x e to the negative x. And observe that f of n would be n e to the negative n, which is an. So by our theorem, the limit as n goes to infinity of an must be the same as the limit as x goes to infinity of f of x. And f of x is x e to the negative x. And x and e to the x, those are differentiable functions. They're continuous and differentiable. They're nice as nice can be. So I can do all the normal L'Hopital's rule stuff here, right? Now this, I'll remind you kind of how this is done. This again looks like infinity times 0. So I need to put it into a form where I can use L'Hopital's rule. L'Hopital's rule only applies to indeterminate ratios. Those are fractions where the top and bottom are either both going to 0 or both going to infinity. And if I rewrite x e to the negative x as x divided by e to the x, now I can apply L'Hopital's rule, because this, as x goes to infinity, looks like infinity over infinity. And like 0 times infinity is not well defined, could have many values. Infinity over infinity is not well defined. It could have many values. Right? That's why we call it an indeterminate form, because you cannot, from this expression, just infinity over infinity, you cannot from that expression infer the value. You can't cancel infinities. This is not 1. So this is called an indeterminate ratio. And what L'Hopital's rule says is that if you have an indeterminate ratio, an expression limit where the top and bottom are both going to infinity, or the top and bottom are both going to 0, and the top and bottom are both differentiable functions, then you can take the derivative of the top, which in this case would be 1, and take the derivative of the bottom, which in this case would be e to the x, and try again. So I will, after this, just do a quick review of L'Hopital's rule. It's going to be quick. Now, after applying L'Hopital's rule, I have 1 over e to the x left. That's lim x to infinity 1 over e to the x. That's 1 over infinity, which is 0. So the limit of the an is 0. And the big trick there was to use our theorem to get from somewhere I can't differentiate, like take derivatives, to somewhere I can differentiate and take derivatives. Now, with all this said, in the future, I will just apply L'Hopital's rule or whatever rule directly to the sequence, because the only effect of this theorem, the only impact it has on what you write down is that instead of writing the letter N, you write the letter X. I could have skipped this step, right? And just done all of this with N's instead of X's. It wouldn't have hurt anything. I would have run through the same procedure and been looking at the same sort of expressions, just with a different variable. The catch is that when you get to the L'Hopital's rule step where you're taking a derivative, technically we shouldn't be taking the derivative of n. And technically, here we would be taking the derivative of e to the n. It wouldn't make sense to do that. But symbolically, it makes sense. And through this theorem, we can justify doing it. Just with the understanding that really when we apply L'Hopital's rule to a sequence, or apply any of these other rules that involve differentiation to a sequence, what we're actually doing is pretending it's a function of a continuous variable and differentiating that. So L'Hopital's rule shows up a lot. There are a handful of problems in your current homework set that require it. Therefore, I think it's prudent to do a quick review on L'Hopital's rule and indeterminate forms. So first, the theorem itself. What it says is if f of x and g of x are differentiable, and the limit as x goes to somewhere, let me just call it c, of f of x over g of x looks like infinity over infinity or 0 over 0, right? Like if f and g both go to infinity or f and g both go to 0, then this limit can be recalculated when x goes to c. F of x over g of x can be recalculated as the limit of the ratio of the derivatives. As you take the derivative of the top and the derivative of the bottom, and try again. That's what L'Hopital's rule says. Now, those two particular indeterminate forms I wrote down these are indeterminate ratios. Ratio just means fraction, right? So indeterminate ratio means a fraction whose value cannot be inferred from the symbols itself. There are many other kinds of indeterminate forms, and the way we handle them all is by smashing them with the algebra hammer until they look like indeterminate ratios, and then applying L'Hopital's rule. That's a mild exaggeration. There are some other things that we do, but that's the vibe, right? That's the vibe. So your list of indeterminate forms, and I'm going to try not to forget any of these. 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, And I think infinity to the 0 would also land here. Yeah. So these first two are indeterminate ratios. This is called an indeterminate product. This is called an indeterminate difference. And these three are called indeterminate powers. And in each one of these expressions, what's going on is that the things are fighting each other, right? Like being 0 upstairs, that wants to make you 0, wants to make the fraction 0, but being 0 downstairs wants to make the fraction infinity. So these are fighting each other. Or if you replace 0 in your brain with very, very small number and replace infinity in your brain with very, very big number, if you take a very, very small number and divide by another very, very small number, you might get a normal sized thing. Or if the top number is considerably smaller than the bottom number, then you'd get a very small thing, something close to 0. If the bottom number is extremely small, smaller than the top number, then you would get a very big number. So these two are fighting each other. And the same thing's going on with the infinity over infinity. If the top and bottom are both really, really big, then they could cancel and get something of normal size. Or if one of those infinities is much bigger than the other, then you could get 0 or something very large. 0 times infinity, very small number times very large number, could be a normal size number. Or if the very small number is like way smaller than this is big, you could get something close to 0 out. If this number is way bigger than this is small, you could get something big out. They're fighting each other. Infinity minus infinity, same thing, they're fighting each other. 0 to the 0 is a fun one. The base being 0 wants to make the whole thing 0, right? 0 to any power is 0. But the power being 0 wants to make the whole thing 1, because anything to the 0 is supposed to be 1. So these guys are in conflict. Same shit here, base being 1 makes the whole thing 1, but raising something to the infinity power wants to make it big. If this is a constant, like if the 1 is actually just the constant number 1, not a function whose limit is 1, then this would be 1. But if you've got some function here that's going to 1 and some function here that's going to infinity, then those are fighting each other. And the same thing here, right? If the base is getting really, really big, but the power is getting really, really small, this wants to make you close to 1 in size. This wants to make you big as fuck in size. So who wins? These are all indeterminate for those reasons. The way you handle any of these is by doing algebra to turn them into these. And I'm going to look at a few examples with you. You don't always need L'Hopital's rule. So let's start gentle. I'm going to investigate the convergence of the sequence AN defined by AN equals the natural log of 2n plus 7 minus the natural log of n. If we just jump right in, just a reasonable thing to try. So just go ahead and say, okay, I'm going to take the limit as n goes to infinity of AN. I want to know if this sequence converges, and that's always what that means. For a sequence to converge means that the limit exists and is finite. That would be the limit as n goes to infinity of this whole thing. Natural log of 2n plus 7 minus the natural log of n. Well, as n gets bigger and bigger and bigger, going to infinity, so does 2n plus 7. So this inside here is going to infinity, and the natural log of infinity is infinity. Just like this. And then, of course, n is going to infinity here. So this is also the natural log of infinity. And that is infinity minus infinity, right? We talked about limits of the natural log function when we were talking about improper integrals. So this is an indeterminate difference, right? This is infinity minus infinity. It's indeterminate. So we have some options, things we can do here. I said I was going to start with an example where we don't need L'Hopital's rule. So indeed, no L'Hopital's rule will be needed here. What is called for? Does anybody have an idea as to how I can get this limit? Okay, it's a logarithm rule thing. So the natural log of A minus the natural log of B can be rewritten as a single log with the insides divided. All right, remember those combine the logarithm problems from your algebra classes? This is like that. Or logarithmic differentiation from your Calc 1 class. Hopefully you saw that there. And from here I have some choices. I could say, okay, well, the limit, right, can go inside the natural log. The natural log doesn't have any bearing on that. So this is the natural log of the limit as n goes to infinity of 2n plus 7 over n. You can shove limits in and out of continuous functions. That's another result from Calc 1. And then this 2n plus 7 over n, that is an indeterminate ratio. That's infinity over infinity. So if I wanted to, I could apply L'Hopital's rule in here. But I don't need to. You can split this fraction up. As 2n over n plus 7 over n. And then 2n over n is 2. And of course, 7 over n goes to 0 as n goes to infinity. 7 over infinity, that is 0. So this would be the natural log of 2 plus 0, or just the natural log of 2. If you want to, you can leave the limit outside the log. You don't need to actually write it coming inside, but that's the logic, right? And that it is a valid step. But the logic here is we just need to figure out what the inside is doing. And you've got a lot of ways you can do that. You can use the renormalization trick. You can use L'Hopital's rule. You can split up the fraction because it splits up very nicely. That's not always possible, but because the downstairs here is just a single term, it is easy to do. But this is an example of an indeterminate difference that we can sort out without using L'Hopital's rule. And especially in the context of sequences, we do like to avoid L'Hopital's rule if possible. An example where we cannot escape L'Hopital's rule could be something like calculate. Oh, we didn't finish this. So sorry, we need to finish here. We need to say, so the sequence AM converges to this number, the natural log of 2, which is about 0.69. All right. Yeah, an example where we cannot escape the L'Hopital's rule is something like limit n to infinity n cubed over e to the n squared. Well, let me see. Possible to write it as the natural log of 2n plus 7 minus n? No, that would not be correct. So the logarithm rule that I'm using here is that subtraction outside is division inside, and it does have to be like that. So there is no rule that tells us subtraction inside a logarithm is the same as anything else outside, just that subtraction outside is the same as division inside. So having the logs, like log of 2n plus 7 minus log n isn't the same as log of 2n plus 7 minus n. So here, the top is going to infinity, right? Infinity cubed is definitely infinity. What's the bottom doing? So the top we said is going to infinity. Downstairs, n squared, this is e raised to the power of n squared. And n squared is going to infinity for sure. This is like infinity over e to the infinity, which is infinity over infinity, which is an indeterminate ratio. So I am allowed to break out some L'Hopital's rule. Oh, this is going to be horrendous. Let's see. Let's see what happens. So if I apply L'Hopital's rule, the derivative of the top would be 3n squared. And this is what I mean when I said I'm not going to actually go through the process of replacing by x. You can just go ahead and work with n's. But it's with the understanding that we're really pretending that we're replacing n by x and differentiating a continuous function. Downstairs, the derivative of e to the n squared is e to the n squared times the derivative of n squared, which is 2n. There's an n downstairs and an n squared upstairs. There's a factor of 3/2, the 3 over 2, that can come out. And what's left is I'll cancel that n and I get n over e to the n squared. All right, so there's a 3 upstairs, there's a 2 downstairs. That means there's a factor of 3/2 in this thing. I can pop that 3/2 out. Here it is. There's an n squared upstairs and an n downstairs. I can cancel those. So there's just one n upstairs now. And the e to the n squared piece hasn't gone anywhere. But the top is still going to infinity, and the bottom is still going to infinity. This is like 3/2 times infinity over infinity, which is again an indeterminate ratio. So in order to handle this guy, I'm going to do L'Hopital's rule again. I still have my 3/2 there. Lim n to infinity, we use good notation, we always write our limits. The derivative of the top, if I differentiate just n, just like if I differentiate just x, I get 1. And the derivative downstairs is the same thing it was before. It's a chain rule derivative. So you get e to the n squared times the derivative of n squared, which is 2n. I can pop the 2 out if I want and say, okay, this is 3/4 times the limit as n goes to infinity of 1 over n e to the n squared. But now the top is constant. The top is just 1. And the bottom is going, well, this piece goes to infinity. This piece goes to infinity. So this is 3/4 times 1 over infinity. And that's 3/4 times 0, which is 0. So pretty standard L'Hopital's rule problem here. And this is usually how I'd expect you guys to do it. I don't require you to replace the n's by x's and be formal like that. You can just go ahead and work with the n's, that's fine. You do need to, every time you're about to apply L'Hopital's rule, verify that the thing you're working with is an indeterminate ratio. If it's not an indeterminate ratio, you can't use L'Hopital's rule. And then my other little bit of advice here, comparing this problem to the last problem, is just that check and see if L'Hopital's rule is necessary. There are many situations where L'Hopital's rule is allowed, but it's not necessary. And some examples where you can solve the problem much, much faster, just doing some algebra, like the top one. Row, I have not, no, but I can take a quick look at that right after class. The 3/4, so I had this 3/2 out front from this first L'Hopital's rule where I got a 3 upstairs and a 2 downstairs. So I said, okay, I'm going to pull the 3 and the 2 out, 3 coming from the top, 2 from the bottom. So I got a 3/2 at this step. And then I noticed that I need more L'Hopital's rule because the thing that was left over is still going to infinity over infinity. So I apply L'Hopital's rule one more time. And when I take that, I have a 2 downstairs. Yeah. So this is like 1/2 times 1 over n e to the n squared. And that 2 comes out as a factor of 1/2, multiplying by 3/2 to give me 3/4. Cool. All right. Other questions, comments on this one? Okay. I have one last L'Hopital's rule thing to show you here, and I want you to pay very careful attention to this one because there's a problem in your homework set that is quite difficult, very important for you to do and understand. And if you pay attention to this one, you'll be able to do that one. You just need to be very careful as you do it. I'd like to calculate the limit as n goes to infinity of, in fact, let me get rid of the plus one. Let me make this as simple as possible. Just the nth root of n. This is kind of strange because when the inside gets big, you know, like if you think of just a square root instead, the square root of n would go to infinity, right? Square roots get big as the inside gets big. It just takes a little while, kind of like the log. But as the root goes to infinity, that wants to make things small. And if you compare the square root of 2, the cube root of 2, fourth root of 2, fifth root of 2, sixth root of 2. Those are getting small. Not going to 0, but going to 1. So there is something strange going on here. And I would begin by just writing this as n to the 1 over nth power. The base here is going to infinity, but the power is going to 0. That's an indeterminate form. It's an indeterminate power. Right? The base wants it to be big, but the power wants it to be 1, wants it to be small. There is no nice way to attack this problem directly, but it can be attacked indirectly. And what I mean by that is, and this is how you handle all indeterminate powers. Before you do any sort of L'Hopital type stuff, you need to make a decision. And that decision is to work with the natural log of this thing instead of the thing itself. So taking the limit of an on its own produces a problem, right? Just gives me this indeterminate power. And there isn't any like algebra I can do to clean this thing up. It's pretty impenetrable. This 1 over nth power, there's nothing I can like do with that. There's no way to FOIL it out or divide it away or anything like that. But if I take the natural log of this thing and work with that instead, now there are rules for logarithms that will allow me to bring this power out here, and now we can start doing stuff. So when you encounter an indeterminate power, your first step is going to be to hit the brakes, go back to the start, and work with the natural log of that object instead. And we're going to try to calculate the limit as n goes to infinity of that, the natural log of a. And at the end, we'll undo the log. Since an is n to the 1 over n, this is lim n to infinity, natural log of 1 over n. And then we have another rule for logarithms. Says that the log of a to the b is the same as b times the log of a. Now this works for any base log, but here we're using a natural log. So this is like a and this is like b, right? You've got something inside the log and it's all being raised to this power. So that power can come down in front of the logarithm, and I get limit n to infinity 1 over n times the natural log of n. And if you try to take the limit at this step, the 1 over n piece is going to go to 0. The natural log of n piece is going to go to infinity. This looks like 0 times infinity, which is an indeterminate product. So I still can't do any L'Hopital's rule because I don't have an indeterminate ratio. You need 0 over 0 or infinity over infinity to apply L'Hopital's rule. I can turn this thing into a ratio, and this is what you do for all indeterminate products. You turn the product into a ratio by shoving one of the pieces downstairs as its reciprocal. So having 1 over n out front like this is the same as dividing by n, like this. Now, as we take our limit, the top and bottom are both going to infinity. And that's good news. That's good news because now we can apply L'Hopital's rule. And like I said, I'm not going to go through the steps of writing x's instead of n's. We're just going to remember in the back of our mind that we can differentiate these things kind of symbolically. Just use your normal rules. We don't need a quotient rule here because I'm not differentiating the whole fraction. L'Hopital's rule says take the derivative of the top and the bottom separately as their own things, which is nice. That makes life better. The derivative of natural log of n would be 1 over n. And the derivative of n would just be 1. And now when you take the limit, you get 0 over 1. And that's not indeterminate. That's just 0. But that's not the answer to my question. We chose to work not with an, but with the natural log of an, because that allowed us to do some stuff. That allowed us to bring this 1 over n out. Whereas before we couldn't do shit with it. But if the limit as n goes to infinity of the natural log of an is 0, no. We can deduce that the limit as n goes to infinity of an itself would be e to the 0, which is 1. Right, and what I'm doing here is I'm undoing the logarithm. And you can make this look scarier if you want to, but the idea is just if you've got a natural log of something in here, and that's equal to a number, right? Then the thing without the natural log is going to go to e to that number. If you want to be more formal about this, you can stick the limit inside the natural log and get natural log of limit of an equals 0. And then exponentiate on both sides. And get e raised to the ln of an equals e raised to the ln of, or e raised to the 0. And so the limit of the an's, you cancel the natural log with the exponential, and you get limit of the an's is e to the 0, which is 1. You get this expression. But this is fine. And this is how I would like your solutions to look in the exams and study guides, homework, as you work through the homework practice, writing out at least these steps, right? This is the minimal amount of work. Any questions on this one? Okay. So we can use L'Hopital's rule for sequences. And that's a consequence of that theorem that says, you know, you can think of, if you can find a continuous function that agrees with your sequence, then you can treat your sequence like that function. One of the other consequences is that you can use the squeeze theorem, right? Basically, all of the theorems about limits from Calc 1 can be imported into theorems about sequences via that theorem that I referred to at the very start of class. if you think of that theorem from the very start of class as a machine that takes in statements about functions, continuous variable functions, and spits out statements about sequences, and you feed that machine the original squeeze theorem, it will spit out the following. If an is less than or equal to bn is less than or equal to cn for all n sufficiently large, right? Meaning like eventually, past some point, this inequality is true and it stays true. And the limit as n goes to infinity of the lower bounding guy is equal to the limit as n goes to infinity of cn, the upper bounding guy. Say they're both equal to the number L. Then the limit of the guy in the middle must also be equal to L. Okay, and this is just like the squeeze theorem for functions. It's literally the same thing. The idea is you're handed some sequence bn and told to take the limit of it. But as you work with bn, you're like, something wrong. For whatever reason, I can't take the limit directly. Maybe there's a DNE somewhere. Maybe there's something like bouncing back and forth or blinking back and forth and being positive and negative, or for whatever reason, the limit of the bn seems difficult to come up with. But it can be bounded above by some sequence that's easy to find and bounded below by some sequence that's easy to find. And both of those bounding function sequences have the same limit. And then the limit of the middle guy has to be that value as well. The example I have in mind for this, let's investigate the convergence of the sequence, I'll call it an, about sine of n over n squared. If we just try to write down the limit, so I want to say whether the sequence converges or diverges. If it converges, I'd like to say what it converges to. So of course, that means I need to take the limit as n goes to infinity of an, which will be the limit as n goes to infinity of the sine of n over n squared. The bottom, of course, is going to go to infinity, but the top, this does not exist. Convergence. Yeah, word right after investigate the convergence. So when I say that phrase, investigate the convergence, I mean, tell me everything you can. Tell me whether this thing converges or diverges. If it converges, tell me what it converges to. Tell me as much as you possibly can. I'm going to pull up Desmos really quickly here. So do I still have my sequences thing? Yeah. This is a pretty nasty one. Let's just look at the sine function. All right, so the red dotted graph, that's sine of x. And the black dots, that's the graph of sine of n, the sequence, just the numerator. And what you see is that this thing bounces around. It bounces all over the place. But what it doesn't do, these black dots are not getting closer to any particular value. There's no no horizontal asymptote here. So the top, dne. Right? As n goes to infinity, sine n is a dne. The bottom is going to infinity. And dne over infinity is not a well-defined expression. So this is a big old question mark. But it is a good hint that we should use the squeeze theorem. In particular, you notice that the top is bounded. Right? Those black dots, they never go out of this window from -1 to 1. So we can use the squeeze theorem. The squeeze theorem relies on an inequality. You have to have an inequality of this form, and you have to tell me for what values of n that inequality is true. The natural place to begin here is with the sine function. And we're thinking of our domain here as being like 0 to infinity or 1 to infinity. Let me say following greater than infinity. If the sequence couldn't start at 0. But this is certainly always true, right? The sine function, no matter what you're feeding it, x's, n's, whole numbers, puppies, no matter what you feed the sine function, it's always going to output a number between -1 and 1. And if I divide through this expression everywhere by n squared, my sequence, sine of n over n squared, will show up in the middle. And that's what I want, because that's what the squeeze theorem is designed to help me. And this is also true, and this is still true for all greater than or equal to 1. So now this guy and this guy, can I tell what their limits are? So the limit of n goes to infinity of -1 over n squared, -1 over infinity, which is certainly 0. And that's the same as the limit of 1 over n squared. So both the lower bounding sequence, the -1 over n squared sequence, and the upper bounding sequence, +1 over n squared, both of those go to 0. But our inequality and the squeeze theorem the limit as n goes to infinity of sine n over n squared equals 0. And we've done all the work, but we do still need to write down the answer. They told us to investigate the convergence of this sequence. So I need to say whether the sequence converges or diverges. So what can you tell me about this sequence AN? Does it converge or diverge? Yeah, very good. Converges. And we can say that it converges to the number 0. Let's see. Sorry, I'm feeling pretty sick. Yeah, so that sequence converges to 0. I'd like to look at another example now. And this is one where we could use the squeeze theorem, but I'm going to give you a simpler tool to use in certain special cases. So let's calculate the limit as n goes to infinity of 2 times -1/3. This is a certain type of sequence called a geometric sequence, and I will discuss special named sequences on Friday. But just taking the limit of this guy at a glance is a little bit tricky. So here, I'm going to begin by showing you some algebra steps that are important to understand for this and other problems. And then we're going to introduce a little theorem. This section 11.1 has a lot of theorems. If you haven't looked at it in the textbook, I want to strongly encourage you to do that. But yeah, lots. So definition of a limit, of course. There's this theorem that we had, continuous variable functions, relationships between those and sequences, and then lots and lots and lots of theorems that tell us how sequences behave. The theorem I'm going to give you here is this one, but there are many more. So I encourage you again, read the section. Read the section. I will give you everything you need, but reading the section, I hope you understand it better. So, first thing I notice is that I can pop out the 2. All right, the 2 is a constant multiple. And then what's left is -1/3 to the n. There's a bunch of ways you can think about -1/3. I can choose to think of it as -1/3. And then raising that whole thing to the n is the same as raising -1 to the n and raising 3 to the n. Perfect. Powers play nice with multiplication and division. They don't play nice with addition or subtraction, but they do play nice with multiplication and division. And this sequence has the same sort of problem that the last sequence did. The bottom is going to infinity, but the top, -1 to the n, that's a DME. And in some senses, -1 to the n is nicer than the sign of n, but in other senses, it's worse. So -1 to the 0, -1 to the 0 is positive n. -1 to the 1 is negative n. -1 squared is positive n. -1 cubed is negative n. -1 is positive n. And it just keeps doing this. And it's not a nice curve, right? This is not the same as the sine of n. I don't immediately have an idea like what curve would fit here. Sure, I could make something work, but I don't have an immediate candidate. what f of x would be here. Can't use -1 to the x. This is not a well-behaved function at all. So it's not as simple as just replacing the n with an x here. Because this thing, good luck. But just see what Desmos says. Where do I? Oh, it's over here. It's gonna oh, yeah. So if you try to graph f of x equals -1 to the x, I don't even know if it's going to try it. Yeah, look at this. Some weird shit going on there, let me tell you. And depending on how zoomed in you are, it might just poop the bed entirely. The weirdness that's going on here, the reason Desmos is having such a hard time even figuring out what to do is because for most numbers you could plug in for x, you're not going to get a real number out, right? Like what is f of 1/2? It would be -1 to the 1/2. That's the square root of -1. That's I. Just try plugging in pi. Good luck figuring out what -1 to the pi is. There is a way to do it in terms of complex numbers, but I'll tell you it's not pretty, and it does not yield a graph. And the best case scenario, you get that thing that Desmos showed us right away, which was that smattering of dots in weird places. It's just -1 to the x ain't gonna play the game. I could do a squeeze theorem thing here. So because -1 to the n is always going to be either -1 or +1, I could say that this sequence is bounded below by -2/3 to the n and bounded above by +2/3 to the n. So we could use the squeeze theorem. Saying that -2/3 to the n is less than or equal to 2 times -1/3 to the n is less than or equal to +2/3 to the n. Right, that is a true inequality that puts the given sequence in the middle, where both the left and right guys are going to the same place. They're both going to 0. So this would work. But there's another way involving absolute values. So this guy on the right is actually the absolute value of the guy in the middle. And I'm going to convince you of that in a moment. And you know, absolute values are always greater than or equal to 0. So I could swap this with a 0, swap this for its absolute value, and this would just stay this. There's a whole bunch of things you can solve this way. And the end result for all of them, going through the squeeze theorem, looks exactly the same. The end result, you realize, is that to say the sequence AN has limit 0 is equivalent to saying that the absolute value of that sequence has limit 0. So if instead of working with AN, you work with the absolute value of AN, you will get 0 either way. This only works for 0, and it's only useful if the sequence you're working with gets nicer when you take absolute values. So why do I introduce this here in the middle of this example? Well, because the absolute value of this thing is actually very nice. And I want to talk to you a little bit about the algebraic properties of the absolute value function. So returning to that example, I'm going to just let an be 2 times negative 1/3 to the n, and choose to work with the absolute value of an instead, which would be the absolute value of 2 times negative 1/3 to the n. We will be using the absolute value function pretty extensively in this section, and more so when we talk about series, and more so still when we talk about power series. So it's time for us to start learning the algebra of that thing. This is something that we talk about in college algebra and pre-calculus class, but everybody forgets. So I'm not going to chastise you for not remembering. I am just going to work through this and simplify this absolute value here and tell you the general rules as we go. And I want you to remember those general rules. We observe that the numerator of my sequence here is a DNE and the denominator goes to infinity. So I think probably the limit is 0. I think probably this is true, but I can't show it directly. And I'm too lazy to do the squeeze theorem stuff. So instead, I'm going to work with that absolute value expression instead and show that this is 0. If I can show that the limit of the absolute value is 0, then by my theorem, it's true that the original limit is 0 as well. This is the limit as n goes to infinity of the absolute value of 2 times negative 1/3 to the n. First things first, absolute value is multiplicative. That means is if you've got the absolute value of a times b, that's the same as the absolute value of a times the absolute value of b. Of course, the absolute value of the number 2 is the number 2. So this is a constant multiple and it will pop out. I get 2 times the limit as n goes to infinity of the absolute value of. We argued correctly earlier that negative 1/3 to the n is negative 1 to the n over 3 to the n. And now, in addition to being multiplicative, playing nice with multiplication, the absolute value function plays nice with division as well. You can take the absolute value of the top and the absolute value of the bottom separately. So I get the absolute value of negative 1 to the n upstairs, and downstairs the absolute value of 3 to the n. Three to the n is an exponential, right? This is a constant base raised to a variable power. Those are always positive. So this is definitely positive. So I can lose the absolute values downstairs. Upstairs, another fact about absolute values, because they play nice with multiplication, they automatically play nice with powers. Powers are just repeated multiplication. So I get 2 times the limit as n goes to infinity. The bottom we said, because 3 to the n is positive, the absolute value of 3 to the n is just 3 to the n. Upstairs, the power being inside the absolute value here is the same as the power being outside the absolute value, like that. And what is nice here is that the absolute value of negative 1 is 1. So this is 2 times the limit as n goes to infinity of 1 to the n over 3 to the n. Before you take that limit, recognize that 1 to the n, this is just the constant 1. And if you raise 1 to the 2, to the 3, to the 4, to the 5, if you raise the constant 1 to any finite power, it will always just be 1. So algebraically, this is equal to limit n to infinity 1 over 3 to the n. And that limit is 0. This is 2 times 0, which is 0. Therefore, since the limit as n goes to infinity of the absolute value of an is 0, it follows that the limit as n goes to infinity of an itself is 0. And you're done. I took the time to write out every little step here. And I did that because I want to illustrate and explain what's going on with the absolute value function. But of course, this could be done much faster. You could jump straight from here, I think without any hesitation, to here. And then from here, without any hesitation, to here. And thus your answer. What this does is it avoids the squeeze theorem, right? This keeps you from having to set up any inequalities. Any questions on this one? Okay. So before I let you go, I want to take this just one little step further. I want to generalize just a little bit, Friday, we're going to be talking about sequences as well. There's still a chunk of material from the sequence section that we're not ready for. Definition. A sequence is called geometric if it can be written in the form an or whatever is some constant, I'll call it a0 times r to the n. The sequence we were just working with was geometric. Generally, when I write this, I'm assuming that the sequence starts at n equals 0 rather than at n equals 1. If you don't like this notation, you can just write an a here. You don't have to call this a0. But as I have it set up, if you let the sequence, if you let n begin at 0, then a0 really is a0. It's because, r to the 0 would be 1. So these terms look like a0 is just a0. A1 is a0r. A2 is a0r squared. A3 is a0r cubed, and so on. These should remind you, if you look for the kind of corresponding function of a continuous variable f of x, that will be an exponential. These are the sequence version of exponential functions. R, which for an exponential function would be called the base, right? Like if I had r to the x, that's a base r exponential. In this context has a different name. It's called the common ratio. And the reason we call it the common ratio is because if you divide A3 by A2, right? Imagine you divide this by this, the A naught would cancel and you get r cubed divided by r squared. That's just r. So if you take an plus 1 and divide by an, right? If you take a given term and divide the next term by that, this would be a0 r to the n plus 1 divided by a0 r to the n. Cancel the a0s, you will just get r. So we call it the common ratio because if you form a ratio of two consecutive terms, it'll always give you that number. Okay. Why are these special? Well, because they show up a lot. Just like exponential functions show up a lot in regular calculus stuff, geometric sequences show up a lot when studying other sequences, and they form a nice basis for comparison. If I want to talk about how fast a given sequence is growing or something like that, I can try to find a geometric sequence that grows at about the same speed, that sort of thing. Also, they're pretty easy to work with, which is lovely as well. The very last thing I'm going to do for you here is give you a theorem relating to geometric sequences, the proof of which would come from the theorem on absolute values. So the geometric sequence an equals a0 times r to the n will converge to 0 if the absolute value of r is strictly less than 1. And diverge if the absolute value of r is strictly greater than 1. And there's a bunch of other ways to say this, but I'll leave it like that. The main thing is the first part. You might wonder what happens if r is positive 1 or negative 1. If r is equal to 1, then an equals a0 times 1 to the n is just constant. So that would technically be a convergent sequence. If r is equal to negative 1, then an is a0 times negative 1 to the n diverges. Because it would just be a naught, negative a naught, a naught, negative a naught, negative a naught. Right? It's the negative 1 to the n thing again. A full rigorous proof of this is within grasp. We could do it. But I want to give you just a partial proof. One, because we're out of time, but two, because again, the important part is understanding when these go to zero and why. Suppose R is between 0 and 1. And think about the function f of x equals r to the x. That function is a normal exponential function. And if r is between 0 and 1, then that's a decaying exponential function. Think of the graph like e to the negative x. That's the same as 1 over e to the x, or 1/2 to the x. These all have graphs that look like this. I have a graph. The limit as x goes to infinity of f of x, which is the limit as x goes to infinity of r to the x, is 0. Therefore, if an is a naught times r to the n, by our theorem from the start of class, the limit as n goes to infinity of an would be the limit as n goes to infinity of a naught times r to the n is a naught times the limit as n goes to infinity of r to the n on its own. Has to be the same as this guy. That's the theorem from the start of class. Then x to infinity r to the x, which would be a naught times 0, which is 0. So if r is between 0 and 1, then the geometric sequence an equals a naught times r to the n converges to 0. If -1 is less than r is less than 0, apply the rule that says lim n to infinity an equals 0 if and only if lim n to infinity absolute value of an equals 0 and the above to get lim n to infinity a naught r to the n equals 0 also. And these two cases cover the first half of the theorem, saying that if the absolute value of r is less than 1, then the sequence a naught times r to the n will go to 0. The best way to remember all this, so that's it. That's where I'm not gonna go any further into the proof. We don't need the full proof. But the way to remember this as lim n to infinity r to the n. There's a few possible cases. The most important one is 0 if absolute value of r is less than 1. 1 if r is equal to 1, and divergent if it's -1 or the absolute value of r is bigger than 1. And again, the truly important part is the first part, that if r has absolute value smaller than 1, then r to the n will have limit 0. These other things do matter as well, of course, but this is the one that we're going to use in a heavy conceptual way, in addition to just using it to solve problems in the homework set. So you have a bunch of stuff to do in your homework, and there are still a few things that we haven't discussed. So 27, 28, and 29, we haven't talked about how to do those. Let me point out a couple others that I don't want you to be worrying about until Friday, and then I'll let you go. If you need to go, by all means, go. Obviously, the stuff in the homework that you can't do is the stuff I haven't introduced yet. You'll recognize it as such. But just in case you've been fretting, I can take a second here to show you. All of these we can do. But there's some stuff involving factorials that we do not know yet. So like number 15 here, don't worry about this until Friday. I need to show you what that exclamation point means. If you already know what that means, you can play with it. 15, 16, 17, those have to do with recursive sequences. We haven't talked about those yet. I'll talk about them on Friday. 18, 19, and 20 you can do. 20 is the problem I was referring to earlier that I said you need to be very careful about. Treat this the same way we did the nth root of n problem. The rest of these, oh, no, here we go. 24, we don't know this yet again because we don't know the factorial yet. 27, 28, yeah, okay, so 27 and on, you don't need to worry about yet. 24, you don't need to worry about yet. 17, 16, 15, you don't need to worry about yet. Everything else, fair game. So please work as many of those as you can. Try to understand them as deeply as you can. If you need help with anything, of course, you can come by my office hours. Otherwise, I will see you guys on Friday when we're going to talk about recursive sequences. And we're going to talk about a theorem on bounded monotone sequences, which will also involve the discussion of this exclamation mark symbol. So that's it from me for today. Take care, guys. And if you need anything, reach out.